Hi everybody, welcome to part 1 of nuclear chemistry. Today, we will use this machine to cut the ethanol molecule. Now, I drew this machine so that I can cut the ethanol molecule and the simplest parts and see what is the simplest form of all matter, at least the ones that we know. So first of all, let's move the machine scale from the molecular level down to the atomic level. So the atomic level, and then pull the lever, and then now I picked out the hydrogen atom. The hydrogen atom is about 53 picometers in the radius, or 106 picometers in the diameter. This means that 106 trillionth of a meter is one hydrogen atom, or approximately 0.1 nanometers. So now that we got to the atom, let's go down to the nucleus and the electrons. So let me move the scale down to the subatomic level. And then activate the machine and see what happens. Turns out, the hydrogen that I picked out was an isotope of hydrogen called deuterium, or hydrogen 2. Now, deuterium's nucleus contains a proton and a neutron. The number of protons also decides its atomic number, which is on the periodic table, the number you see like 1, 2, or 3. Now, the neutrons help stabilize the atom, but also destabilize it if too much or too little neutrons come in. Now, the electrons orbit it also make the element get its properties. For example, the fluorine atom has one empty spot in its electron configuration. So it looks like this. There's one empty spot, but it would be a lot quicker to just get one electron instead of kicking all of these out of there. So fluorine and all the halogens will most likely accept electrons. On the other hand, an atom, such as lithium, has only one electron in its outer shell. It will most likely just give away this electron rather than take 7 electrons inward. So it's going to give away electrons. Here, hydrogen has its first shell, but the first shell can be completed with 2 electrons. So it can become a cation or anion. But also, it's actually not really like this. It doesn't orbit the atomic nuclei like our solar system, but more like a cloud or blades of a fan. So the electron is spread around in this cloud. Where it can also bond with other atoms, say hydrogen. Also, this explains the Pauli exclusion principle, which states that no 2 electrons can stay in the same place at the same time. So that's enough for now. Let's move the scale down to the level of the quarks, which is as smallest as we know it. Phew. Okay, I broke the machine a little bit, but that's okay. Okay, so I split the atom. Now, I actually got a lot of these balls here that are bonded. Now, the blue ones are called the D quarks, which are short for down quarks. Now, the orange ones I drew are called U quarks, or up quarks. As we know, electrons cannot be split just yet. But quarks these are the only quarks that exist. We also have 4 other types of quarks, called the charm quark, strange quark, top quark, and the bottom quark. But these 4 of them quickly decay into the commonly known up quarks and down quarks. In other words, they are very unstable, and a lot a lot of people, or maybe all people, never really see it. In fact, quarks have never been observed directly. But how do we know all this stuff? Well, in part 2, we'll see how people thought of the atom throughout the ages, such as from all the way to ancient Greece, where the atom was discovered, and all the way to today. But for now, well, this is our video. Until now, it was Ethan's laboratory. And thanks for watching the Nuclear Chemistry Part 1. See you in Nuclear Chemistry Part 2. Bye!